Good evening. Now, yesterday we have seen maximum part of Unit 1. Now we have some part of Unit 1, some part of Unit 2. What is slab? Now students are saying what is slab, then they are confused. What is slab? Slab is a two-dimensional member. We have slab is a two-dimensional flexural member, I can say. Because column is one dimensional, slab is two-dimensional flexural member. So keep in mind we have slab two-dimensional, footing three-dimensional, and beam and column one-dimensional. I will repeat: beam and column one-dimensional. Then we have slab two-dimensional. Why one-dimensional? Because two dimensions are very less, means your length is very large compared with its width and depth. Why slab is two-dimensional? Because depth is very less compared with other two dimension. And we have footing three-dimensional. We have footing three-dimensional. Footing three-dimensional. So that is most important. We should know what is slab flexural member, what is beam flexural member, what is column, axial and axial plus bending. We have combined loading. And footing again we have flexural member. What are different types of slab? Now this is most important question we can say. So we have types of slabs. Now we are going to divide it into two parts. You have to answer very properly. So considering end conditions. Considering end conditions. End conditions. You have to write in this or you have to answer in this way. Considering end conditions, we have simply supported. Then we have cantilever. And third we have continuous. Now considering Ly by Lx ratio. Ly by Lx, we have two types. One, we have one-way slab. And second, we have two-way slab. Now, what is major difference between these two? One-way slab supports on two edges, on two long edges. And therefore, if we have slab in this fashion, so we have supports on this side. So long edges we have support, and therefore how it will bend? So it will bend in this fashion. Because it support only on long edges. But two-way slab support on all four edges. Supports on all four edges. And therefore, it bends on both sides. Saucer types, we have its bending. So it will bend in this fashion. And then it will bend in this fashion also. Means from both sides. And therefore, we have in this MUX and MUY. Here we have only MU. And here, therefore, we have main reinforcement along short edge. main reinforcement along short edge. Along short edge. This is most important. Here we have main reinforcement along both edges. Main reinforcement along both edges. So here distribution reinforcement is not required in two way. Here we require distribution reinforcement. And what is distribution reinforcement? So it is reinforcement provided for secondary stresses. Provided for secondary stresses. Now secondary stresses means we have creep, we have shrinkage, then we have temperature stresses. So for these secondary stresses, we are going to provide distribution reinforcement in one-way slab. Two-way slab, we have reinforcement, main reinforcement along both direction. Now, two-way, again, we are going to divide into two parts. Two-way slabs. So we have two-way slabs. One, we have a restrained slabs, table number 26. Restrained slabs. And second, we have simply supported slab. Simply supported slab. Now in a restrained slab, we are going to restrict lifting of corners, or corners are not allowed to lift up. Not allowed to lift up. And therefore, we have to provide torsion reinforcement. Now, what are values we have already seen in video? I will not go in that one. You should know which corner we have what value. In simply supported, corners are free to lift up. Corners are free to lift up. Lift up. And therefore, no torsion reinforcement required. No torsion reinforcement required. So as we are going to restrain corners, and therefore what will happen? Torsional moment will develop. Torsional moment will develop and will be developed. And for that, when we have to provide torsional reinforcement, as we are allow corners to lift up, no restraint, and therefore what will happen? Corners are free to lift up, and therefore no torsional reinforcement required, because torsional moment is not developed. Torsional moment is not developed. Is not developed. Now, in both the cases, formula for MUX already we have seen, alpha x WLX square. So this is most important. And MUY, we have alpha y WLX square. In both we have LX, because LX we have span. LX is span, and this is shorter dimensions. So this for both we have same, that is for span moment. And for support moment, we have in restrained slab, it will be alpha dash WLX square, alpha dash WLX square. Now alpha x, alpha y, alpha x and alpha y for restrained slabs, we have 9 cases. 9 cases given in table 26. In simply supported, we have only one condition, which is given in table 27. This simply supported, we have rare condition. If we have only one slab, then only we will come across this condition. Then, what are the steps involved? So we have first step, that is effective span. Now you should know clauses. I will not go to it. Effective span, go to videos, you will come to know effective spans for simply supported, for cantilever, and for continuous. For continuous. In continuous, we have two cases. That is L by 12, that is width, less than width, and do another we have greater than width, up to 600. Then second, we have trial depth. Now for trial depth, already we have seen how we will find it. So we have L by D ratios. We have 7 for cantilever. We have 20 for simply supported and 26 for continuous. Then we have to multiply it by modification factor. Modification factor, we have modification factor. Now just see, I don't exactly remind the figure. I think check it, figure 4. And we have to select the curve. How we will select curve? So we have Fs equal to 0.58 into Fy. It is given area of reinforcement provided upon area of reinforcement required. We are assuming that value 1, and therefore we will consider it Fs is equal to 0.58 Fy. And from this we are going to assume, or we are going to finalize depth. Finalize depth. Then we have third. So after finalized depth, you have to again go for effective span. Now we have two criterias. In first criteria, we have center to center distance. Here we have center to center distance. And we will give it number 1. And in second, we have clear span plus effective depth. Number 2. And minimum of the 2 we have to consider. Then third we have, that is load calculations. You should know steps of all, that is beams, staircase, column and footing. All footings, 4 types. So load calculations, then we have to go with self weight plus, which is also known as dead load. Then we have floor finish. So these both we will say as dead load plus live load. And then we have to find out total load from this. And knowing total load, we are in position to go for bending moment calculations. Then depending upon your beam, we have to find bending moment. Now for cantilever, so see very carefully, we have WUL square by 2. This is total load WU. For simply supported, we have WUL square by 8. And then we have for continuous. Now we have to check, can we use, we have two methods for this. We have to go IS code coefficients. IS code coefficient. Or we have to go moment distribution. Moment distribution, same as beams. Then after this bending moment, we have to go fifth, check for depth from bending moment. Check for depth from bending moment. Most of the cases we will have greater than 6. We have reinforcement. should know the formula. You have to mug up it. So we have AST equal to 0.5. Write down once, twice, FCK upon Fy in bracket 1 minus root of 1 minus 4.6 mu upon FCK BD square whole into B into D. Then we have seventh. So here we have, this will be main, I will mention. And this should be greater than AST minimum. AST minimum class number you should know already given. 0.12% of gross area B into capital D. Keep in mind, not a small d. Here we have to consider gross cross section. And then this is for FE 415 and 500. For FE 250, we have this value 0.15%, again gross area. So these are the main steps. Then we have to go for check for shear. So you can say we have not done it. I don't have any problem. Check for shear. Then we have check for development length. Check for development length. In slabs not required. Up to 6, we have more than sufficient. So we have these steps which we have to use in slabs. What is distribution reinforcement? Already I mentioned, it is nothing but secondary reinforcement. Secondary reinforcement. And what is value of this distribution or secondary reinforcement? So this is minimum reinforcement. Minimum. And I already mentioned this is for secondary stresses. Already I wrote this one. Secondary stresses, creep, shrinkage, temperature, likewise. Shrinkage, temperature. This is most important. We should know all this. So steps important. You should be in position to design. While going for check for depth, so we have to find RU max, and we know formula for RU max. Otherwise, we are confused with 0.36 FCK KU in bracket 1 minus 0.42 KU. So this formula I should know, or I have to mug up it. So likewise, we have to go with questions related with your slabs. So now we will stop here only. Remaining part we will see in the next video. So thank you.